Today's lecture deals with the problem of having unknown interest rates or periods. We've looked in previous lectures at calculating, for example, an annuity given a present worth, or a future value given a present worth, or a gradient, converting a gradient to annuity. But always for given interest rates or number of periods. But quite often you'll have problems where it's the interest rate or the number of periods that's unknown. So I want to do a couple of examples and show you how that calculation works. Here's a problem. What interest rate will result in $5,000 7 years from now, starting with $2,300 today? So you're given a present worth of $2,300 today, a future value of $5,000, and you know that the period is 7 years, but you have to calculate the interest rate. So for example, this might be you're wanting to save up $5,000, and you know how much should you invest it at to get that money? Well, we have our compound amount formula. Relating a present worth to future worth. If we substitute these values in, we get $5,000 is $2,300 times 1 plus I to the 7th. Taking the 7th root of both sides, we can get 5,000 over 2,300 to the 1/7 is going to be equal to 1 plus I. And simplifying that, we get I is equal to 5,000 over 2,300 to the 1/7 minus 1 equals 0.11732, or 11.73%, which is fairly straightforward. However, it worked in this case because we were lucky enough to be able to isolate the I to solve it. That's not always the case. And that's where linear interpolation comes in handy. I'll show you how to do the same problem and get the same answer, or a close answer, using the tables of values for compound amount factors. Now, what we'll do is we'll use a variation on that compound amount factor. We'll say that future worth is equal to the present worth times the symbolic form of the factor, f/n I% n, and solve for that compound amount factor itself. And we've got then 5,000 is equal to 2,300, and 7%. I'm sorry, that's I% for 7 years. Isolating that compound amount factor, we get f/p I% 7 is equal to 5,000 over 2,300, which is equal to 2.1739. Now, what we're looking for then is an interest rate that gives a value for this compound amount factor of 2.1739. If we look in the back of the book into tables of compound amount factors, chances are we aren't going to get this number exactly. What we're going to get is numbers bracketing, like one's larger and one's smaller than that number. So I've looked in the book, and I find that for 11% interest, the factor gives a value of 2.0761, and for 12% interest, it gives 2.2106. So just by observation, we can see that the desired interest rate is somewhere between 11 and 12. And perhaps for one particular purpose that might be sufficient information. But if we want more information than that, we can use our linear interpolation. Because what we're given is a known relationship between the independent variable, which is I, and the dependent variable, which is the value of that transformation function, for two particular points. And we're also given the value of the dependent variable at one particular point without the corresponding value of the independent variable I. So on our little chart, what we know is 11% and a corresponding value of y, 12% and a corresponding value of y. We know a particular value, y prime, and we want to calculate this x prime. And that's our linear interpolation problem, and we can use our linear interpolation formula. So we want our x prime, and what we've got is an x1, which is the value of interest for the lower amount of 11. So that's 2.0761. Excuse me. It's 11 times the difference between the x's, which is 1, between 11 and 12. 12 minus 11. And all that's times the difference between our the value of y corresponding to the unknown value of x we're looking for, which is 2.1739, minus the lower value of 2.0761, divided by the differences between the two values of 2.2106 minus 2.0761. We're looking for the unknown interest rate, so we know the x's are the interest rate. That's why this is an 11, this is the 12, and this is the 11 again here. The dependent variable is the y, is the value of the compound amount factor, and that's why the value of 2.1739 and so forth is over here. If we work out this particular calculation, we end up with a value of 11.727%. Now, this value of 11.727% is slightly different from the value calculated from basic principles of 11.73%. The difference is quite small, but it's because of the nature of that function. Recall that with linear interpolation, we're approximating the function by a straight line. The actual function is some curve, which is different from a straight line. And so there's going to be a slight error in our value of x, our value of the interest rate in this case. But as you can see, that error is fairly small. And in general, if you get your known values reasonably close together, it's by and large natural to expect that the linear interpolation will give a fairly good result. Let me give you one more example of an unknown period problem. Here's where Clem buys a house for $47,000. He puts $7,000 down on the house. That means he pays the $7,000 right away, and agrees to pay the previous owner $1,000 per month at 12% nominal interest. So this is a mortgage. It's a conventional way of buying a house. And what we want to know is how long it will take him to pay back the mortgage. This is the amortization period that you often hear talked about. It's how long it would take to pay off a mortgage at a particular amount of money. Generally, when you buy a house, you pick the amortization period of, say, 20 years, and then calculate the monthly payment. But sometimes you might want to choose a monthly payment that you can afford and then calculate the amortization. This particular case was actually how I bought my first house, this exact deal. And the owner liked it because she wanted to use that mortgage as her her everyday monthly expenses. And having it large like that was useful to her. Now, we've got a present worth of $47,000, which is not the present worth we want to use because the $7,000 down subtracts from that, leaving really a present amount of $40,000. We want to find the equivalent annuity to that $40,000 at $1,000 a month. We have an interest rate, but we don't have the number of periods. But we're relating a present worth to an annuity. We have two formulas for doing so, the series present worth formula or the capital recovery formula. In both cases, and there are very similar formulas, it's going to be extremely difficult to isolate that n. And in fact, I think it's possible, but only because someone else has shown me a way of doing that in a previous class. But it certainly isn't very easy because it appears both in the numerator and the denominator as an exponent. And in both cases, there's other elements in either the numerator or the denominator that makes it very difficult to for example, like the nth root of both sides of an equation. So this is another problem in which it can be quite useful to use the linear interpolation. Now, what we have is an annuity of $1,000, and that's going to be equal to the present worth of $40,000 times the capital recovery formula. For a known interest rate of 12%, but we're working on a monthly basis, so that's 1% per month. Because it's nominal 12%, recall with nominal interest rate, we simply divide by the number of periods in the year. And an unknown interest rate n. Again, what we want to do is isolate that compound interest factor. And then we look up in the 1% interest table for values of n that bracket, that is to say, are larger and smaller than the amount we're aiming at. If we look in the interest table, we find that at the 50-month mark, the value of the capital recovery factor is 0.02. 552, and I made a mistake up here, of course. That's 0.0250. And for the capital recovery factor at 55% interest, it's 0.02373. Linearly interpolating, we're looking for the n. So our n is going to be the lower bound of 50 plus the difference between the two values of 55 minus 50 times the dependent variable values, the target of 0.0250 minus the lower 0.02552 over the higher bound 0.02373 minus 0.02552. So in running through this calculation, we get the answer of 51.45 months, which is 4 years and 3.45 months. So for Clem's house buying problem, this was a very good deal for him if he was able to afford the $1,000 per month because he pays off the house in a very, very short period of time. And in his negotiations, he was able to use the desire by the previous by the vendor to have these high monthly payments to make a good deal for himself. So by being able to calculate this, was as useful information for him in his planning. Now, another thing to mention is this 3.45 months doesn't really make that much sense in calculating an annuity, because annuity by definition is an even amount per month. But what this would really come down to in practice is that the last month payment would be either higher than normal if it's paid in the end of the third month of that year, or lower than normal if it's paid in the fourth month of that year. And it's reasonable to report the number of periods in that way anyhow. So there's two examples of dealing with unknown interest rates and periods. You can do it either from direct principles mathematically, where it's feasible to do so, but where it's not, linear interpolation is extremely handy. Whether you do it manually as I did here or have it programmed into your personal calculator doesn't really matter. But it's a useful technique. One thing I'd like to mention too is that you can always go back and check your value for accuracy by plugging your calculated value for the interest rate or the number of periods back into the original formula. And make sure that the approximation that's engendered here, because it is an approximation being linear interpolation, is accurate enough for your purposes. Thank you.